We have just shown that we could write separate Hamiltonians for each mode with no interactions between the modes. Since the energy eigenstates for the individual modes are just number states, that is, a specific number of photons in an individual mode, the energy eigenstates of the full electromagnetic field correspond simply to specific numbers of photons in each mode. So, when we want to write an energy eigenstate of the full electromagnetic field, we simply need to write down a list of the numbers of photons in each particular mode. And of course, we can use these energy eigenstates as basis states in any problem for describing the electromagnetic field. We could call this way of writing down the states the occupation number representation.
For example, the state with 1 photon in mode K, 3 in mode M, and none in any other mode, which would be an example of a multimode state of our electromagnetic field, could be written in the following form. So we have 0 photons in mode A and so on, up to 0 photons in mode J, but then we have 1 photon in mode K, none in mode L, 3 in mode M, and none in any of the other states. So we can simply write this multimode state as a list like this, all inside a ket vector. And we've labelled our modes, as we've said, progressively here just using the letters of the alphabet in lowercase. Just as before, the annihilation operators will have the property, now specific to a given mode, that if we operate on this multimode state that has n lambda photons in mode lambda with the annihilation operator, then what we will do is end up with n lambda minus 1 photons in mode lambda, and of course we'll get a square root of n lambda out front. And if we happen to have 0 photons in mode lambda, of course the annihilation operator operating on that would give us 0, or technically the 0 vector here. Similarly, if we use the creation operator for mode lambda on this multimode state here that has n lambda photons in mode lambda, then we will increase the number of photons in mode lambda by 1 to n lambda plus 1, and we'll also acquire the square root of n lambda plus 1 out the front. And the number operator for a given mode would similarly be the creation operator times the annihilation operator. And that operator operating on a state that had n lambda photons in this specific mode would give us the number n lambda out front times that same state. Now, we can create a multimode state by progressively operating with the appropriate creation operators. We start with the 0 state or empty state, which we often write simply as this. And now we mean by this, of course, that there are no photons in any modes. And for our example state we had talked about before, we could write, instead of this list here, where we had put 1 photon in mode K and 3 in mode M and none in any other state, we could write instead this form. Here we've started with the empty state. We've created 1, 2, 3 photons in mode M and 1 in mode K. And the factor here, 1 over the square root of 1 factorial times 3 factorial, compensates for all the factors introduced by the creation operators in this kind of relation, so we can keep the state normalized. So we progressively had introduced these factors every time we operated with the creation operator, and we're dividing out by them to keep the state normalized. In general, we can write a state with n1 particles in mode 1, n2 particles in mode 2, and so on, as a state like this. We can write it out just in its occupation number representation. And in general, we would have all of these different numbers of creation operators all in a row here operating on the empty state, and all of these factors down here to keep the state normalized.